Oh,
hello,
and welcome to the Institute of Physics East Anglia branch's lecture series. I'm Colin Ribton. I'm the chair of the East Anglia branch, and we're looking forward to our lecture this evening, which is from Niladri Banerjee, and we welcome him to the East Anglia area. If you have a question, please put it into the Q&A box, and we'll get round to all of them at the end of the talk. And also be aware that this lecture is being recorded and will be uploaded onto the IOP Region and Nations YouTube channel, so it can be enjoyed in the future. So it's my pleasure to introduce our speaker for this evening, Niladri Banerjee. Niladri is at Loughborough University. He's a senior lecturer in the Department of Physics, and he started there with a Vice Chancellor's lectureship in 2016. He graduated with a PhD in Materials Science from the University of Cambridge in 2011, and from 2011 till 2015, he was a postdoctoral research associate in Cambridge and a junior research fellow at Wolfson College. At Loughborough, his research in experimental condensed matter physics focuses on studying the interaction between magnetism, superconductivity, and spin-orbit coupling. I'll now hand over to Niladri, and I will see you all after the talk for the Q&A.
Thank you very much, Colin. Can you hear me now? Am I audible?
Yeah, we can hear you.
Okay, that's great. Okay, thanks a lot, Colin, for the kind introduction, and thanks to everyone in the IOP East Anglia branch for organizing this. It's a pleasure to be here, although virtually, but still, it was supposed to be last year, but due to all the COVID, so it's taking place this year. But so it's a real pleasure to be here, and so today I'll be talking about superspintronics towards ultra-low dissipation spin electronics. And my research in Loughborough is being sponsored by the PSRC and the British Council. So the way that I'll introduce superspintronics would be from a slightly application point of view, but when we go through as I present the results, I'll also show you that this is beyond application. This has also many fundamental aspects that we are investigating in our group. So if you look at the energy forecast, the global energy forecast in the information and communication technologies, what you will see is over the last 20 years, so starting from 2010, this is a prediction till 2030, it is growing exponentially. And a significant part of this is taken up by this green section that you see on the plot, which is the data centers. As you know, nowadays, because of Facebook, Google, and all the softwares that we use, everything is now stored in cloud. So that has its own advantages, but the major sort of the driver for the energy in this sector is taken up by the data centers, and it is going to only grow in the future. Now, what is the problem with that? The problem you can partly see here. The Facebook data center is located somewhere in Sweden, and you can see that the outside temperature is significantly below room temperature, and there is a reason for that, because all the supercomputers are in these data centers. They generate enormous amount of heat, and that heat has to go somewhere. So ideally what they do is that they place it in an environment which is already, say, to start with, at -20 degrees. So it's a lot easier to cool the data centers. So that partly shows the extent of the problem here. Sorry, I'll just switch back to the arrow, which might be a bit easier. Okay, yeah. So you can already see the problem, and this image, for example, shows the Google data center in Oregon, and you see the extensive cooling that is required to sort of maintain the data center at a reasonably operating temperature. If you look at the internet traffic, that has grown from 1987 to 2017 by 10 orders of magnitude. So it started at around 2 terabytes, and now if you look at it, it's 10 to the power. So it is a massive increase in the internet flow, which is also going to increase in the future. So the main problem is this heat dissipation that is occurring in these data centers, which partly we can get the feeling of it in our laptops as well. So as you start your laptop and you start working in your laptop, you'll see that it warms up. And this is orders of magnitude more for a data center. So what we need now is not only a cooling technology, so it's not a trivial problem of cooling the data center. We need to rethink how we process data and how information is processed and stored. So there are several approaches to do this. One is called spintronics, which I'll introduce and I'll explain, and the other one is superconducting electronics, which I won't get any time to introduce, but all these are sort of partly addressing the problem. So in this talk, what I'm going to show you is that superspintronics, which is a combination of superconductivity and spintronics, is probably at a position which can address most of the problems. But it comes with one critical caveat, is that it is nowhere near sort of application. So it will not even in the midterm we can apply this technology in the data center. So the US has put forward an effort to build a superconducting supercomputer. So what we can hope for is maybe in the next 10 years or beyond, some components of superconducting spintronics starts to get some application in these superconducting supercomputers. Okay, so what the outline of the talk is, I'm going to briefly introduce ferromagnetism and spintronics, and then I will move on to the basics of superconductivity. And then we will look at some introductory superconducting spintronics, look at key experiments that have been done over the last 10 years and the progress where the whole field stands. And to conclude, I'll show you that a series of recent discoveries which shows that spin-orbit coupling, which is a relativistic phenomenon, that plays a fundamental part in superconducting spintronics and the work that we have been doing over the last few years on this area. And then finally, I will conclude with the open questions and an outlook. Okay, so this is a terrible diagram to introduce the densities of states. So what do we mean by densities of states? So this is room for electrons to stay in a solid. So for example, if you have copper, if you take copper as an example, you'll have, these are now red colored persons and green colored persons, and they have two buildings to go into. And you see that the bottom two floors are already filled up by people. So they cannot enter these filled up rooms. So they can only go into the rooms that are empty. And the second condition is that the red guys can only go into this building and the green guys can go into this building. So as they move, the red guys are going to populate these rooms and go out of the building, and the green guys are going to populate these rooms and go out. So in a nutshell, what it means is that we started with 3 red guys and 3 green guys, and what comes out is 3 red and 3 green. But imagine a scenario where the number of rooms are not equal. So the red might have a more number of rooms compared to the green one. And there is an option that once a person gets in, if they cannot fit in the green building, they have the option of changing the color and going to the red building. So if now red has more rooms, say if red has 5 rooms and green only has 1 room available, then the natural thing for the green persons to do is that they get inside the building, change the color to red, and get accommodated here. So whatever comes out now will be more red guys than green guys. So the densities of states for electrons reflects this number of available rooms, and the colors, they represent the spin of the electron. So now if we move on to a slightly more realistic, what is known as a band diagram of a metal, a normal metal like copper. So you see the distribution of the energy versus the densities of states. So densities of states, again, to reiterate, is a number of available rooms in the building. What we are injecting here is a finite number of electrons with up and down spin electrons. And since they have equal number of rooms for the up and down spin electrons, what comes out of the metal is also equal number of red and green electrons. Simply, I mean, the electrons are not really red and green, but I've just colored them for convenience to denote that these are spin up and spin down electrons. And now spin is a quantum mechanical property. I mean, this has no sort of classical analog, and you can simply sort of think the spin as a magnetic moment pointing either up or pointing down. So here it is colored as green and the red. So this is all good. What it means is that it's a charge current. So it's a current of electrons. When you inject it into a copper, what comes out is also a charge current of electrons. But the key, there is no difference, that the spin was 0 to start with, so there was no net spin. What comes out, there is no net spin. However, if we now look at a ferromagnet, which is in the ordinary sense, the fridge magnets that we see, for example, iron, cobalt, or nickel. If we now look at ferromagnet and inject a spin 0 charge current into the ferromagnet, you notice there is a difference now. All the empty rooms, denoted by these and then by this horizontal line, it has fewer number of red spins to go into, the rooms for the red spins to go into, compared to the green. So what happens is, mostly what comes out, you see that there is an excess number of green electrons or spin up electrons. So what we injected to start with was a charge current with spin 0, and what comes out is a finite spin polarized current. So it carries a finite spin, or it carries a finite magnetism. You can think in analogy to optics, you can think it as a polarizer. It polarizes the current. Now, just by using this ferromagnet and non-magnet, we can develop something called the spin bulb. Now, the spin bulb is a foundational sort of device of spintronics, and I'll explain in a second why. So now what you have is two ferromagnets separated by a non-magnetic metal. Now, imagine that both these ferromagnets are pointing up. So the magnetic moment is up. So now we inject a spin 0 charge current. The first ferromagnet is going to obviously spin polarize the current, which means that whatever comes out goes into copper as excess number of upspin electrons. They are now injected into the second ferromagnet, and they are happy because it is pointing in the right direction, so they come out. Now the problem is, if the second ferromagnet is pointing in the opposite direction, you inject a spin 0 charge current. The first layer polarizes the spins of the electron. Copper is happy to transmit all the spins, but as the upspin electron or the green electrons tries to enter the second ferromagnet, they are scattered more because the ferromagnet is not pointing in the right direction, it is pointing in the opposite direction. So the downspin electrons will be more favorably passed through the ferromagnet compared to the upspin electrons, as a result of which you will have increased amount of scattering in the ferromagnet, leading to a high resistance state of this device. So if we plot the resistance as a function of magnetic field, we start with a positive magnetic field where both the layers are parallel. The resistance remains low, spins are less scattered, and as we hit the magnetic field where one of the layer flips, we can tune the layer when one of the layer will flip so that both doesn't flip at the same time or at the same magnetic field. If we take care of that, then one of the layer will flip, and this leads to an anti-parallel state where the resistance is high, and then again you increase the magnetic field in the negative direction sufficiently so that then both the layers are parallel in the opposite direction and the resistance will come down. So this change in resistance is significant, and this was known as the giant magnetoresistance, which was discovered in the mid-1980s towards 1988, and by two independent groups led by Albert Firth and Peter Grunberg, for which they were awarded the 2007 Nobel Prize in Physics. And this led to this field called spin-based electronics. Now, why is it spin-based? Because if you take a step back and look at this, this is a device which is sensitive to the spins of the electron. Because I was talking that this is a low resistance state and this is a high resistance state, but I haven't really discussed about current, the voltages or anything to do with charge-based stuff. I was always talking about magnetism. So this is a device where the resistance can be tuned just by adjusting the magnetic moments, which is purely due to the spin of the electron and nothing to do with the charge of the electron. So we have developed something, a device, which can detect a change in resistance, or you can induce a change in resistance by keeping the magnetic moment, which is only sensitive to the spins of the electron. Now, the question is that what is the advantage of doing this? The obvious advantage is that in a charge current, you will have a lot of scattering, which gives rise to a material's resistance, which obviously leads to Joule heating and everything heats up. But if you have a current of spins, then spin scattering is far less frequent than momentum scattering. And because of that, anything operating on spins will have much less dissipation compared to its charge counterpart. So if we can design devices which works purely on the spin of the electron, then we can develop a technology which is far less dissipative than the charge-based electronics. Now, it doesn't stop here. Spintronics gives a sort of fundamental insight into how spins interact with matter. So this is one application, but this is not, if you do not look from an application point of view, if you focus on the fundamental science of it, there's a lot that spintronics offers, and our ideas of how spins interact with matter has been revolutionized by spintronics for the last 2 to 3 decades. Now, the next thing that we are going to look at, and the reason that we are going to look at that is it is completely not dissipation less, because although you're generating a current of spins and everything is fine, you are still using an initial charge current. You're still using a current of electrons to inject into this first ferromagnet so that it gets spin polarized. So there is some dissipation in the circuit. You haven't completely eliminated that. Now the question is that can we use superconductors? Because we know that superconductors are material which has zero resistance. As you cool down the material below the transition temperature, the charge current can flow without any resistance. So what if we can replace things with superconductors? Can we then retain the advantages of spintronics and still go dissipation-less? So let's look at that. So in a superconductor, things are quite different. As you can see that the band diagram of the energy versus the densities of states look very different. And the key difference is that there is a gap at the Fermi energy. What is the Fermi energy? It is the energy at 0 Kelvin, where all the states below the Fermi energy are filled up by electrons, and all the states above the Fermi energy are available for electron transport. So if you inject an electron at 0 Kelvin, when there is no thermal smearing, the electron will go at an energy which is higher than the Fermi energy because all the rooms below are filled up. So in the superconductor, there is a gap in the Fermi energy. What that means is if you inject a charge current, so that is a current of electrons with spin 0, so there is no net spin, we still get out a charge current which is spin 0. But the only difference now is that you see that the spin up and the spin down electrons are paired up. And these are known as Cooper pairs. And because of this pairing, the state is a stable state and it doesn't undergo any scattering as a normal metal, as electrons in a normal metal would do. So you can have dissipation-less current in a superconductor. So injecting a spin 0 charge current, forming Cooper pairs, you are extracting still a spin 0 charge current, but this is now dissipation-less. So it can flow without any resistance. And the theory of superconductivity was provided by Bardeen, Cooper, and Schiffer in 1950s, and they were awarded the Nobel Prize in Physics in 1972. I'll not go into too much details of how Cooper pair forms, but a very vague description of the formation of Cooper pair is that if an electron is moving in a lattice, so the purple colors are the ion cores that you see. So if one electron is moving in that ion core lattice, it will slightly draw, as you can see here, it will slightly draw all the ion cores towards itself. Because it has a negative charge, the ion cores are positive, so it will be slightly drawn towards the electron, which means that a second electron sitting here When it looks at this area, it will see a slight concentration of positive charge because positive ions are crowding here, and it will get attracted. And it is this attraction that helps them to form a pair, which is known as the Cooper pair. So which is good. Now we have removed dissipation, so we can do spintronics. Almost. Let's see the problem with doing spintronics. So this is a data from a superconductor. Just I showed that the resistance goes to 0, and the temperature of transition, you see it's around 6 Kelvin. So it is very low, so minus 267 degrees. It is a niobium sample. Okay, now, so what do we have? We have Cooper pairs, which is 0 dissipation. But the problem that you see here is that although it is 0 dissipation, that each Cooper pair is spin 0 because it is made up of a spin up and a spin down electron. So it cannot carry any information. In spintronics, we were encoding information in single electron spins, but we won't be able to do that if we use Cooper pairs. So what we ideally need is these sort of Cooper pairs, where the spins are pointing in the same direction. And this, in the language of quantum mechanics, is known as triplet Cooper pairs. And these are singlet. So we can, if we use triplet Cooper pairs, we can transmit information. But what is the problem of using triplet Cooper pairs? I mean, we have magnets which can polarize all the spins. So why not inject a singlet Cooper pair into a ferromagnet? The problem is that if you have a singlet Cooper pair and you apply a magnetic field, the singlet Cooper pair breaks up. So it no longer flips and becomes a triplet Cooper pair. So that is a major problem. So if you inject them, they will not form a triplet Cooper pairs, but they will simply break and lose the superconductivity. We are going to go into the details in the next few slides. So I'll leave it here, and I'll quickly go back and show you that how these films are deposited. So when we work with these systems, these films are very thin films. What do I mean by thin films? These are a few tens of nanometers, or in some cases few nanometers, and 1 nanometer is 10 to the power 9 meters. So it's extremely thin. It's only a few atomic layers thick sometimes if you use 1 nanometer film. And so these are deposited by a technique called sputtering. There are other techniques to deposit thin films, but we mainly use sputtering to deposit. So there is a target which contains a material that you want to deposit. You strike a plasma, and there is a substrate, and this plasma actually sputters material from the target and deposits on this substrate. And this is carried out in very high vacuum, less than 10 to the power minus 9 millibar, which is 100 billion times less than the atmospheric pressure, to remove any contaminants that can ruin the thin film or the interfaces. And you can control the thin film thickness down to nanometers. So this is a transmission electron microscope micrograph of a thin film that we deposited, which shows that the thin film interfaces are fairly clean. They're not disordered. This is one of the thin film system that we have in Loughborough. And there's a sputtering system where you can deposit 4 different materials. So now let's focus on something known as the proximity effect. Why do we focus on proximity effect? Because we want to understand that, well, this is not possible to inject a singlet Cooper pair into a ferromagnet so that it becomes triplet. We can encode information. So let's see how we can get around that problem in order to make a triplet Cooper pair. So in order to understand that, we have to take a step back and we look at a superconductor and a normal metal. So it can be a niobium, which is a superconductor, 30-40 nanometers in contact with copper, which is a normal metal. So the Cooper pairs will then leak into copper and make the copper superconducting. Because of the proximity, the copper becomes superconducting. And the length scales are often hundreds of nanometers. It's greater than, much greater than 500 nanometers. But if we replace that with the ferromagnet, as we noted that because of the exchange field inside the ferromagnet, the Cooper pairs are rapidly killed inside the ferromagnet, which means that the superconductivity can only penetrate a couple of nanometers into the ferromagnet. Now, this, in effect, it means that you cannot turn a ferromagnet into a superconductor. So you cannot have a magnet which is a superconductor. And there is one more subtlety involved in here. I'll not go into the details, but it might be useful to understand the next phase of the triplet generation, is that when the singlet Cooper pair, represented here by the up-down minus the down-up arrow, enters the ferromagnet, it picks up a phase. What is this phase? It picks up a phase in the waveform. And you can expand that and rewrite that as a singlet Cooper pair, that is up-down minus down-up, which is what we started with, and something called the spin-zero triplet Cooper pair. Now, this is not the triplet that we are looking for. This is still anti-parallel. We are looking for equal spin triplet, both spins either pointing up or both spins either pointing down. So this is a spin-zero triplet that arises in the ferromagnet. It can be used to generate a triplet Cooper pair, which I will show you in the next slide. So the situation in early 2000 was that you cannot inject superconductivity into a ferromagnet. So that's a problem, and there are many physics even with this short-range interaction between a superconductor and a ferromagnet. But there was a surprising theoretical paper back in 2001 which suggested a very counterintuitive idea that one ferromagnet is bad for superconductivity, but two ferromagnets can be good for superconductivity, which is very surprising. But the caveat is that the second ferromagnet, or the first ferromagnet here, which is at the interface between the thicker ferromagnet and the superconductor, either needs to be some sort of an inhomogeneous spiral ferromagnet or needs to be simply misaligned with the first ferromagnet. Now, why is that? I mean, imagine that they are aligned. I mean, if they're aligned, you can as well treat them as a single ferromagnet. So in order to distinguish that, you need something different, and this something is the direction of magnetism of the first ferromagnet. So how does this happen? So if there is a second ferromagnet sitting here, or the first ferromagnet at the interface, what the theoretical paper predicted is that it is in principle possible to convert a singlet Cooper pair into a triplet one. And now I'm not going into the details of how this happened, but for people who are already familiar with this Cooper pair and the quantization, so the first ferromagnet generates a spin-zero triplet that we have seen in the previous slide. And as the spin-zero triplet moves into the second ferromagnet, there is a rotation of the magnetization, because of which they can transform into equal spin triplets. A rather convenient experimentalist view of this is you have a singlet superconductor having up-down Cooper pair, which goes into an inhomogeneous ferromagnet where one of the spins gradually rotates and it becomes a equal spin Cooper pair. And this is what we plan to do. And this now can carry an information because this is either a +1 spin or a -1 spin, in contrast to what we started with, which is a spin 0. Now, it took a surprisingly long time to experimentally verify that. And one of the first verifications came from the group of Mark Lamar in Cambridge in the material science department. And so before we go on to that, that specific experiment, we will not do it historically. We'll rather do it in a slightly different way. Now, the question is that how do we detect the triplets? We are going to come back to the original experiments that detected triplets, but there are various ways to detect these triplets. How do we know that these triplets have formed? One is we can measure the transition temperature of the superconductor, which measures how strong the superconductivity is. The second approach is something called the Josephson Junction, and these are the two I'll discuss. The third and the fourth is a magnetization dynamics and the spectroscopic signatures that we are not going into details in this talk. So let us look at how do we find evidence of triplets by measuring TC, or the transition temperature. So if we have a stack, so we have a ferromagnet, a superconductor, and a ferromagnet tri-layer sandwich, and as you can see, it could be 3 nanometers of cobalt, 20 nanometers of niobium, 5 nanometers of nickel. And if both the ferromagnets are pointing in the same direction, the magnetic moments are same, then the superconductor in the middle is seeing a lot of magnetic field coming from these two layers. And if you measure the resistance, versus the temperature, you will see that this tri-layer stack goes superconducting at a lower transition temperature. So this is the transition for the parallel alignment, in contrast to if it is anti-parallel. If it is anti-parallel, the magnetic fields cancel in the middle, the Cooper pairs are happy, they can stay, and you have a higher transition temperature of the superconductor. So just by monitoring the transition temperature as a function of the magnetic moments, we can understand if the superconductivity is getting weakened or is getting stronger. Now let's see how do we apply that to understand whether there are triplets. So first we did an experiment where we had two ferromagnets, permalloy, which is a standard ferromagnet, and the superconductor in the middle, and you can switch one of the permalloy layers in the opposite direction when the other layer hasn't switched. So this is possible by something called the exchange bias. I'm not going into the details of that. If we note the resistance of this whole stack, you will see that at low magnetic fields, the resistance drops. And the reason it drops is at low magnetic field, the layers are anti-parallel. So both the layers are anti-parallel. Magnetic field in the middle cancels out. More Cooper pairs can survive. And the stack has a higher transition temperature, as we have seen in the previous diagram. So that means that the resistance is lower. But if the magnetic moments are parallel at higher magnetic field, this is minus 20-30 millitesla, high magnetic field, then the fields at the center adds up and you have a lower superconductivity in the middle layer, which means a higher resistance. So just by monitoring the resistance as a function of magnetic field, you can get an idea of whether the superconductivity likes the environment or it doesn't like the environment. We repeat the same experiment, but now with holmium layers at the interface. Now, if you remember what this holmium this holmium is a spiral ferromagnet. I haven't discussed holmium now. So this holmium is a rare earth ferromagnet. We will use this holmium later in Josephson junctions. And this provides, if you remember, this spiral magnetism that was required at the interface. So this is a sort of the first ferromagnet at the interface. So since there is holmium now, you have triplet Cooper pairs in the system because this can rotate one of the spins without breaking the Cooper pair. So now since you have triplet Cooper pairs in the system, you notice what happens to the resistance as a function of magnetic field. It is exactly opposite to what we had before. Rather than a dip at zero field or near zero field, we have a peak at near zero field or low fields, which means that if the magnetic moments are pointing in the same direction, the transition temperature, the strength of the superconductivity is higher compared to when they cancel out, which is very surprising. It's just the opposite. It shows that as if the superconductor likes the magnetic field rather than seeing a low magnetic field. So this puzzled us for a while, and eventually what we realized is now there are triplets in the system. So as you have the two ferromagnets pointing in the same direction, now these triplets are no longer confined within the superconductor. They can leak through the ferromagnet, so they can leak through the first ferromagnet. But the down-down Cooper pairs that you form, they cannot pass, because if you remember, the downspin electron cannot go into a magnet pointing in the wrong direction. So the downspins are reflected back. But if they are anti-parallel, then the up-spin Cooper pair can pass through this layer, and the down-down Cooper pairs can pass through this layer. But notice what happens when the Cooper pair is passing through these layers. You're draining the superconductor out of Cooper pairs. So you're lowering the transition temperature. So although the magnetic field is low, but you're lowering the transition temperature because you're draining the Cooper pairs out. And the reason you're draining it out now is that these are triplets. These can happily stay inside the ferromagnet, pass through the ferromagnet, and you sort of dilute the superconductivity. Before you were like confining it to the niobium, now you have diluted to the whole layer. And that's the reason that the transition temperature changes. So what have we gained from this? I mean, this is a signature that the underlying Cooper pairs that is mediating the transition temperature, that is mediating the transport, is not singlets, because using singlet Cooper pairs, you cannot explain the results. So these must be mediated by triplet Cooper pairs. And this forms a spin valve where you can adjust the resistance, similar to spintronics if you remember, but using now triplet Cooper pairs. Now we look at the second way to detect triplets, that is by using Josephson junctions. Now to explain Josephson junction, so this was discovered by, theoretically predicted by Brian Josephson, who was a PhD student back in the 1960s in the Cavendish lab. And he, during his PhD thesis, came up with this idea, which led to the Nobel Prize in Physics in 1973, that if two superconductors are separated by a non-superconducting barrier, then the superconductivity can still, that the two superconductors can still talk to each other via this non-superconducting barrier. If you remember this proximity effect that we discussed, the copper becomes a bit proximatized because of this superconductor. And then there is the other superconductor here, which also proximatizes the copper, and the copper becomes superconducting. And now the two wave functions can sort of shake hands across copper. What happens because of that? Because of that, there are many surprising physics in Josephson junction, but one of the key things is if you look at the current voltage characteristics, something very odd comes out. Is that for a normal conductor, this is the dotted blue line that you will see, it's an ohmic conductor. You increase the voltage, you increase the current, and there is a linear relationship. But if it's a Josephson junction, you have a current at 0 voltage, which means that Cooper pairs are being transported even when you do not apply a voltage. So that is very surprising. And so Josephson junction has many applications in superconducting electronics. I won't have time to go into that, but we will see that how we use this Josephson junction to identify if we have generated triplets. You can almost guess, I believe. So if we now replace the copper with a cobalt, what will happen? The Cooper pairs doesn't like to go into copper, so they would not go. And the two wave functions from the superconductors, they stop shaking hands across copper, and there won't be any current at 0 voltage. So it will be a ohmic conductor. But the moment we put this holmium layer at the interface, which is a spiral ferromagnet, then what we see is that surprisingly we get back the Josephson junction, even when the cobalt is thicker in the middle, as thick as this one, or even thicker, which would have blocked all the singlet Cooper pairs from going here to here. So the very fact that we see a Josephson junction, or the very fact that this superconductor is talking to this superconductor, means that it must be mediated by triplet pairs. So this was done back in 2010. What they showed, the authors showed that if you insert holmium layers, you get a significantly higher supercurrent through the Josephson junction than if you do not have holmium. The supercurrent quickly decays as a function of the cobalt thickness. What we later showed is that instead of using holmium, you can use a simpler ferromagnet like permalloy, and if it is slightly misaligned, you generate the triplets, which happily pass in your ferromagnet. You apply a tiny magnetic field and you remove that misalignment, and the triplet is killed. Why is this important? Because you have now got a switch where you can turn on the triplet by not applying a magnetic field, and turn off the triplet by applying a tiny magnetic field. So this acts as a switch. I'm not going to go into the details of how we identify that this is a triplet Josephson junction, but very briefly, a normal Josephson junction, if you apply a magnetic field, the critical current oscillates, which is known as a Fraunhofer type oscillation. But here we see more of a switching type in our junctions, where there is no current at high field, where you have aligned everything. There's a high current at low fields, where the two layers are misaligned. So now we see that this is impossible if we assume that the transport is mediated by singlet Cooper pairs through the ferromagnet. It has to be triplets. So this is an indirect proof of the existence of triplet Cooper pairs. There has been a recent experiment, and I won't have time to go into this, but this is a very interesting experiment because we were thinking about how the triplet Cooper pair moves through the ferromagnet, we haven't thought of something is once you generate the triplet Cooper pairs, if you try and inject it into a superconductor, conventional superconductor, a singlet like niobium, how will the triplets behave? Will they be accepted or will they be rejected? What this experiment shows is that the red line showing the density of the triplet pairs, it dies down inside a superconductor, conventional superconductor. So this is very surprising. You generate these triplet Cooper pairs, which are superconducting, but they do not, or they are not supported inside a conventional superconductor. So although they are superconducting, a conventional superconductor doesn't like them or doesn't like the triplet Cooper pairs passing through the superconductor. So it's a very strange form of superconductivity. I mean, these are the fundamental sciences that I was talking about. I mean, although there is an application side, but there is a lot of fundamental physics in there that needs to be explored in this triplet Cooper pairs. The way we do this fabrication of the Josephson Junction is by something with standard photolithography, and we then take a focused ion beam, which is a beam of gallium ion, which is focused down to a sort of few tenths of nanometer, which acts as a chisel, and you can carve out metals. So you can make these nano pillars, which are Josephson junctions. You have niobium on the top and the bottom, and the active layers in the middle. So this is one of the micrograph of the Josephson junction. As you can see, the current comes through here, flows down, comes out. So these are very easy to make. So in the last few minutes, in the last 10 minutes, what I would do is I would focus on sort of what I would like to call a second paradigm shift. Why do I call it a second paradigm shift in superconducting spintronics? The reason is, in the last 25 to 30 minutes, what I've shown you is you can generate triplet Cooper pairs, which is a way around to make a ferromagnet superconducting, but you need 2 layers, 3 layers with complex magnetic alignments. Again, I would like to point out here, I'm taking a different angle, is that I'm trying to put this as a simplification of the device structure. But I'll later point out to you that this is much more than a simplification of the structure, and that's why I call it a second paradigm shift. So we need multiple ferromagnetic layers to generate the triplets, but this is not ideal, right? Because if you try to apply a magnetic field, all the layers will respond to the magnetic field. It will never happen that one will respond, the other will not. So it's a nightmare to work with 3-4 ferromagnets and misalign them. So the idea is that we can use something called the spin-orbit coupling. And what is the spin-orbit coupling? So if you take the hydrogen atom, the simplest possible element, which has a positive charge in the middle, which is a proton, and the electron going around in this classical orbit, the electric field, if you sit with the electron, if you sit on top of the electron, you will see that the proton is going around in circle, and the electric field, the electrostatic interaction between the proton and the electron, will have a magnetic component. And this comes from Einstein's special theory of relativity. I'll not go into the details of that, but the key fact is, if you look from the point of view of the electron, any electric field that it is moving under will appear as partially magnetic. And once you have magnetic field, what will it do? It will interact with the spin of the electron. So what this is doing is it is interacting. This is the orbital motion is generating a magnetic field which is interacting with the spin of the electron. So this is why it is called the spin orbit coupling. But now you can already start to feel that since there is a magnetic field, can we use spin orbit coupling, which will take up the role of this inhomogeneous ferromagnet and just use one magnet and not 2 or 3? This is precisely what we have done. We have got rid of the second ferromagnet, or the first one, and replaced that with a heavy metal, which is platinum. And this platinum is, the reason we have used the heavy metal is that heavier the central charge, more the central charge, more number of protons you have, higher will be the spin orbit coupling. So we have used platinum, which has one of the highest spin orbit couplings. What we see here, again, I will not go into too much details of the experiment, but I'll show you a terrible diagram to explain that what I plan to tell you on this is, if you forget about spin orbit coupling and everything, if you apply a magnetic field to a superconductor, which is in the plane of the film, so parallel to the film, what will happen to the transition temperature? Nothing will happen. If it's a thin film, it will stay as it is because of something called the Meissner effect, which is not favored in this direction. So orbital depairing will not happen if you apply the magnetic field in the plane of the film. If we apply it out of plane, so if you apply perpendicular magnetic field, you will see that the TC will get uniformly suppressed. So if we keep this picture in mind, then we move on to the next slide. This is the experiment that we did. We had a niobium and a platinum layer. We measured the in-plane TC. You see that it more or less remains constant with few millikelvin fluctuation. We put a cobalt layer, which is a control sample with the niobium. You still see that the in-plane TC remains constant. The out-of-plane TC goes down a little bit faster than the in-plane one, than the out-of-plane for the control sample. And the reason is now not only you have the out-of-plane magnetic field, you also have the magnetic moment of the cobalt acting on the niobium. But the moment we include a second platinum layer here at the interface, we generate a ferromagnet which is now spin orbit coupled. So there are two platinum layers on the end, and you can treat the whole sandwich as a ferromagnet with spin orbit coupling. And you see that there is a dramatic difference. The in-plane TC decreases significantly. It is almost 40 millikelvin. So that is 0.04 Kelvin. It may not appear a lot, but in superconductivity it is a lot. And the out-of-plane TC is a lot slowly decreasing with magnetic field. So again, it seems like it is behaving in a way which it likes the magnetic field, out-of-plane magnetic field. Where the conventional superconductor dies, this guy now likes it. So you might remember from previous slides that is a signature of triplets. We did some analysis. I'm not going into the details of the analysis, but the key part that we came out of, which is the interesting part, is that the platinum cobalt platinum, you can think of it as a black box with a magnetization which is slightly tilted. Why is it tilted? Because of the platinum layers. It slightly comes out of plane. And if it is in contact with the niobium layer with lots of Cooper pairs, these are now spin zero Cooper pairs. Because there is a ferromagnet, it is in contact with niobium, it generates a lot of spin zero Cooper pairs, spin zero triplet Cooper pairs. But the key fact here is that if you change the magnetization orientation, what you will see that you generate more and more triplets. So the thing that we discovered is that previously, if you do not have spin orbit coupling in the system, you do not change the population of spin zero triplets. They remain constant. So the spin orbit coupling sort of builds a bridge which helps to tune the population of the triplets by controlling the angle of the magnetization. So if you have noticed, something striking has happened, is that it is again modulating the superconductivity of a niobium layer, but now not by using two ferromagnets, but by using just one ferromagnet. So it is a spin valve, a superconducting spin valve with just one ferromagnetic layer. And this was all possible because you bring in spin orbit coupling into the picture. Why is the reason I call that this is not just a sort of a technical sort of advancement to simplify the device structure? Because spin orbit coupling, superconductivity, and ferromagnetism, these three represent three very fundamental electron interactions. And what we have shown in this experiment is that the three can coexist together, and they can take part in generating this very novel form of superconductivity, that is triplet superconductivity. Just in the last few minutes, I'll show you a consequence of this, which is very interesting. And the reason I say that this is not merely a sort of advancement of the simplification of the device structure. I'll show you something which is not possible without spin-orbit coupling. So if you remember from this, as we take the magnetization more and more out in plane, as we make it more and more in plane, we generate more and more triplet pairs, and the TC of the superconductor goes down because it doesn't like to see triplet pairs. As you take it more and more out of plane, the superconductor is happy because you're generating fewer triplets. Now let's see how we can utilize that. So we initially start with the magnetic moment pointing in the plane of the layer. It is high temperature, so assume it is 12-13 Kelvin. The superconductor is not superconductor, it's a normal metal. The magnet is pointing in this direction. Now you cool down the system below the transition temperature of the niobium. So the niobium becomes superconducting. Now this guy is still pointing in plane. Does a niobium like that? The answer is no, because it is generating more and more triplets, which the niobium doesn't like to see. So what would be the lowest energy state of the system if the magnet flips up? Because that closes the triplet channel. That is what the superconductor wants, because it doesn't want to see the triplets. It doesn't like the triplets. Can the magnet flip? The answer is yes, it can. If the condensation energy of the superconductors, as the superconductor cools down, it releases energy because of the condensation of it, because it turns superconducting. If that energy is sufficient to rotate the magnet. So we predicted that in 2019 in this paper, that it is possible under certain special circumstances that the magnet can flip as you cool down the system. Now, what is so special about this? I mean, since our high school days, we have been learning that you can flip a magnet by using a magnetic field. But notice that we haven't applied a magnetic field here. This is switching a magnet purely by superconductivity without any magnetic field. So that is why this is remarkable. And this shows that superconductivity, usually being much, much weaker in energy than ferromagnetism, can in fact switch the magnetism, so can win over magnetism. This was recently demonstrated. We collaborated with a group in Spain, which has demonstrated that indeed it is possible. We used an iron layer over a superconductor, vanadium, and we monitored the resistance. This was more like a sort of not exactly a Josephson Junction, but similar to that measurement. And the top magnet was used to monitor what the bottom magnet was doing. And what we found is that just as we go below the transition temperature, the ferromagnet moves from here, the minima in energy, rather than moving to here, it develops an additional minima at 45 degrees. So the ferromagnet automatically switches at 45. And recently, in collaboration with that group, we found out that it is possible to switch the magnet in the out of plane direction as well. Right, okay. So now we've come to the end of the presentation. So what I'd like to point out here is that what are the open questions here now? So what we have found is that superconductivity can be used to modulate the magnetic states, right? So now, is it possible to actively manipulate the magnetic states by using a current of Cooper pairs? Because that will be very useful. It can be done in spintronics. It is called spin transfer torque. The question is, can we do it with superconducting spintronics? So that will mean that you can change the magnetic moment of tiny little magnetic bits just by passing a supercurrent. So that can be used as magnetic memories, for example. So the next question is that, can we have functional devices, for example, superconducting triplet transistors? So you see that where it is heading towards is heading towards a complete logic circuit based on triplets. We understand very little about the dynamics of the triplet state. All these experiments are like static experiments, where things are, magnets are not moving. But what happens if it starts to move? What happens if there is an excitation of the magnetization? We don't know. We are just beginning to understand the role of spin-orbit coupling in superconducting spintronics. So there is a lot more to learn. And the next obvious, very exciting question is that, could we have a two-dimensional version of superconducting for spintronics, like the two-dimensional materials that we see now, graphene, for example, van der Waals heterostructures? Can we use these? These are single atomic layer thick materials, can we now bring down everything to just 2 dimensions? And that would be a remarkable breakthrough. Okay, so to conclude, I've shown you that the superconducting spintronics unites sort of the superconductivity and spintronics, which are 2 very different phenomena. But by engineering at the interface, by doing very basic material science, it is possible to generate this novel form of superconductivity. I've also shown you that there could be superconducting spin valves operating on this triplet superconductivity, and you can control the magnetic states with them. Most importantly, there is this, we have named it as superconducting spin orbitronics, because there is a room temperature version of spintronics called spin orbitronics, where spin orbit coupling is important. And we believe that our results and the other experiments that various groups have done since then shows that there could be a superconducting analog of spin orbitronics. Right, so at the end, I'd like to thank all my collaborators over the last 10, 12 years who has helped in various different sort of theory with Professor Jacob Linder, Professor Farhad Aliyev's group in Spain, in Madrid, which we are collaborating now. In Cambridge with Mark Blamar and Jason Robinson, we did a lot of the early experiments. And we collaborate quite closely with the Advanced Light Source in the Lawrence Berkeley labs to do some spectroscopic measurements that I was discussing. And these are the current members in my group, the PhDs and postdocs who are involved in the experiment. So I'll just leave you with the conclusions. Thank you very much.
Thank you, Niladri, that was excellent. And thank you very much for describing so clearly what is a very new science and the very recent developments and emerging developments in an area that I'm sure is going to be very important in a wide number of applications. I've got a couple of questions for you. One was about, you were talking about sort of big currents of electrons where you've got an overall majority of either spin up or spin down. How do you actually detect that? What methods do you use to measure whether your current has an overall spin, as it were?
Right. Yeah. No. That's a very interesting question. That how do you measure it? The easiest way to measure that would be just by using a second ferromagnet, which is a spin valve configuration. So you can think of it as just a polarizer analyzer experiment in optics. So you hold the polarizer, which polarizes the light in one direction. You take another polarizer and rotate by 90 degrees, and you see that everything becomes dark because it blocks all the light. And it's very similar. You use a ferromagnet in one direction to polarize all the spin of the electrons, and then you use a second ferromagnet to, if you orient in the opposite direction, that will block all the electron spins, and the device will be in the high resistance state. So that is one of the ways of measuring. I mean, it's not the only way, but this is the easiest way to measure the sort of the spin polarization of the current.
Yeah, I've got a second one. I think I might know what the answer is, but I think I better let you answer it. Which is, can you use an external magnetic field with a non-ferromagnetic material in order to produce favorable conduction of one spin? Or is there something special about the ferromagnetic material?
Yeah, this is a very interesting question. Yeah, it is possible in the sort of in the sense that if you have a non-magnetic material, if you apply a high magnetic field, you do see that one of the spin bands move up in energy. But the key fact is that the moment you remove the magnetic field, it goes back. So the key thing about ferromagnets are that it can maintain even in the absence of magnetic field. So it is very difficult to get the same amount of splitting that you have in ferromagnets. So to get the same polarization, it's very difficult to apply that high magnetic field in a normal metal. However, you can use spin orbit coupling. So if you have spin orbit coupling in a normal metal, so for example, if you have platinum, and if you pass a charge current, you will see that the electron spins get deflected, and the scattering depends on the spin orientation. So you can get a spin current without applying any magnetic field in a non-magnetic metal. So that is possible. Yeah.
That's great. Great. Well, that's brought us almost up to the hour, just a minute to go. So thank you very much again, Niladri. It's been a pleasure to see your presentation, to meet you. Thank you for that. For everyone else, we'd love to have you join us for more events. If you go to the iop.org website, there are events from all the regions and nations, so that's the UK and Ireland, and they're going on a fairly regular basis. So please check out there. And also, I think as you come out of this, there'll be a quick survey. So I know these things can be a bit irritating, but try to answer the questions as quickly and honestly as you can, because we like to hear your feedback, and we're always keen to improve these events and to make them as good as we can for you. So from me and from Niladri, thank you very much, and goodbye.